In section 6.2, we're going to be multiplying and dividing radical expressions. So the first thing that we're going to go over here, if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b, I can just write under the same radical. What's important to note here, though, is that a and b have to be being taken to the same root. So for our first example here, could I combine the cubed root of 6 times the square root of 2? As you can see here, they are not being taken to the same index or to the same root, so I can't simplify this any further. On the other hand, let's say I'm trying to combine the cubed root of -4 times the cubed root of 2. These are both taken to the cubed root, so I can combine what's inside the radical. -4 times 2 gives me -8. Now I'm taking the cubed root of just -8. And when I do that, I get -2, and I'm done. Before we get into some more complicated problems, a helpful tool that we're going to use is prime factorization. This will be helpful for when we're trying to take cubic roots or anything to the fourth root, where it isn't necessarily easy to see like a perfect cube or anything to the fourth power that could pull out of a higher number. So I guess, for example, to start here, let's say I had the square root of 24 and I wanted to simplify it. If I'm taking the square root, I'm asking myself, what are perfect squares that go into 24? Since we've been working with perfect squares for a while now, even before this class, since like middle school, it's not going to be that hard for you to think of a perfect square that goes into 24. Here, I'd look at that and I think, oh, okay, I could split this up into 4 and 6. 4 is a perfect square. The square root of 24 simplified is 2 square root of 6, and I'd be done. But now, let's take a look at the cubed root of 24. And if I want to simplify that, now I need to think of perfect cubes that go into 24. And now that I'm working with cubics, it's not necessarily going to be as easy to just look at that and see a perfect cube that can pull out. So if I do prime factorization, essentially what I'm doing here, I'm taking 24, whatever number that I have, and I'm going to keep splitting it off into factors until it gets smaller and smaller until I'm left with only prime numbers. Combining all those together is going to be the prime factorization, and that's going to tell me any perfect cubes, perfect squares that can come out of 24. So when I start here, I'll just start by doing 2 and 12. 2 is a prime number, so that branch to the left is going to stop. 12 can keep going. I'm going to split this off into 2 and 6, and then 6 can keep going into 2 and 3. Now, here are all my prime numbers, and I'm done. So 24 can be rewritten as 2 cubed times 3. And what you'll notice there is that now I see, oh, okay, 2 cubed can pull out of 24 when I'm taking a cubic root. Another thing to note with prime factorization is that it doesn't necessarily matter how you split off these numbers. What's kind of cool about it is that no matter how you start it, the factorization that you end up with will always be the same. So for example, let's say instead I split off 24 doing like 8 and 3. 3 is going to stop to the left there. 8 will split off into 2 and 4, 2 and 2, and I have the same values here. So working back into my equation, the cubed root of 24, I'm now going to rewrite as 2 cubed times 3. 2 cubed will pull out of this equation. When I pull it out of the cubic root, it's just left as 2. So my final answer here would be 2 times the cubic root of 3. So now let's work with another example. I want to simplify the expression the cubic root of 54 times x to the 5th power. Since I have 54 here, again, I want to ask myself, what's a perfect cube that goes into 54? This might not be so easy to just think of off the top of our head, so let's use prime factorization here. 54 I'll split off again, and I'll split off again. So 54 can be rewritten as 3 cubed times 2. Now I can see the perfect cube that pulls out. So I'll rewrite my constant number like that. Now I got to deal with the x to the 5th power. Now when I'm dealing with these are a little bit more simple. I'm literally just going to split x to the 5th into x to the 3rd and x to the 2nd, like that, and then the x to the 3rd will just pull out. So now here I'm looking at this equation. Think of anything to a perfect cube. Think of that like the key to like free yourself from the radical, or I guess that's how I think about it. So that 3 has a cubed with it, that can escape. And the x cubed can also escape, and it can now appear outside of the radical. So when I rewrite this value is now going to be 3x times the cubic root of what was left inside, which is 2x squared. And I'm done. So now let's look at a little bit of a harder problem. now I'm multiplying two radicals together. I have the square root of 72 x cubed times y cubed times square root of 10xy cubed. I'm taking the square root of both of these so I can combine these by multiplying them. So I'm left with 720 x to the fourth times y to the fifth. So I have 720 here. In class, we'll go over, since I'm taking a square root, you might be able to look at this and know a perfect square that comes out of it. But if not, let's do prime factorization just to get some more practice. 720 can split off, splits off again. Those are prime numbers, splits off, splits off, splits off. And there we go. So kind of a long one, but that's okay. So 720 can be rewritten as 2 to the fourth power times 3 squared times 5. I'll rewrite that. So I'm taking the square root. X to the fourth, 4 is going to perfectly divide into 2, so I don't actually have to split up anything here. Y to the fifth, though, isn't going to divide evenly into 2. So I'm going to rewrite that as y to the fourth times y. Now I'm looking at things that are going to divide out of the square root. 2 to the fourth will come out as 2 squared. 3 squared will come out as 3. X to the fourth will come out as x squared, and y to the fourth will come out as y squared. All that I have left in here is the 5 and y. So my final answer here, combining now just my constant terms, I have 2 squared times 3 or 4 times 3. My final answer here is going to be 12 x squared y squared times the square root of 5y. One of the last things we're going to do today, kind of the opposite here. If the nth root of a and the nth root of b are real numbers and b is not equal to 0, if I'm dividing those two radicals and they're being taken to the same power, I can put them all under one big radical. So again, important thing to keep in mind, I can't do a cube root over a square root. Those won't combine. Similar to what I talked about with multiplying. So here I have the square root of 18x to the fifth over the square root of 2x third. Since these are both taken to the square root, I'm going to rewrite this as one big fraction. And what's kind of nice here is that I can simplify the fraction, then deal with the radical. So 18 over 2 is going to give me 9. X to the fifth divided by x to the third, I'm subtracting their powers. I'm now left with the square root of 9x squared. This will easily simplify. Square root of 9 is 3. Square root of x squared is x. My final answer is 3x. The very last thing I promise that we're going to talk about in this video is another really important part to simplifying radicals, which is called rationalizing your denominator. So kind of along the same lines as when I dealt with complex numbers, I can't have an imaginary number in the denominator. I don't want to have any radicals in the denominator in any value in simplified form. I don't know why, that's just proper math, I guess. So for example, if I had 3 over the square root of 2, if I want to rationalize the denominator, for this, I'm taking the square root, I'm going to multiply the square root of 2 by itself. That's going to give me to just nice whole number 2. Remember, whatever I do to the denominator, I have to do to the top to keep it the same value. My new answer here is going to be 3 square root of 2 over 2. Again, keep in mind, this is the same value. I just made it so that there wasn't a radical in the denominator. The very last question that we're going to do today is kind of a doozy, so just stick with me. This is the last thing that we're doing in this video. I'm taking the cubic root of 5x squared over 12y squared z. So I'm going to kind of work backwards here in that I have everything under this big cubic root. I'm going to rewrite it to have the cubic root on the top and bottom and kind of work from there. I want to rationalize the denominator, so I'm going to kind of start to break down the denominator to start. You'll see why in a second. I'm going to look at 12 and do the prime factorization here. So 12, I'm going to break up into 3 and 4, then 2 and 2. 12 can be written as 3 times 2 squared. So no perfect cubes there, but that's okay. So now I have my denominator rewritten like this. Now when I want to rationalize it, since I want to get rid of the cubic root, I want to basically cube all of those terms in the denominator. So I want to get everything in the denominator to have something to the third power. So as I'm going through this, 3 right now is being taken to the first power. If I multiply it by 3 squared, I'll get 3 to the third power. 2 squared, I want to multiply by 2 to the first to get that to be to the third power. Y squared, y to the first. Z is being taken to the first power right now, so I'll want to multiply that by z squared to get z to the third power. Again, same thing as before, whatever I do to the bottom, I also have to do to the top, so I'm going to multiply the top and bottom by the same thing. When I do this, since everything's like in a cubic root, I can just multiply everything under the radical. On top, I got that 90 from doing 5 times 3 squared times 2 and just combining everything else. And then on the bottom, now you're going to see I have the cubed root of 3 cubed times 2 cubed times y cubed times z cubed. So all of these are going to come out of the radical, or they're going to simplify, or that cubic root and the cube are going to cancel each other out. So my final answer here is the cubic root of 90x squared yz squared all over 6yz. And finally, I would be done with that problem. Also, good rule of thumb, I know that I'm done and nothing simplifies on the numerator. There's no perfect cubes that come out of 90. You could prime factorize it and check. X squared, y, and z squared, there's no cubes that'll come out of that either. So even though it's kind of ugly, I know that I'm done.